Hi, my name is Michael Whitaker, and this is my talk, A Guarantee Too Good to Be True. Now, I'd like to start with a confession. I was a naive and gullible child. I believed almost everything that movies, commercials, cartoons, and TV shows told me. I believed that special shoes could make a kid run faster and jump higher, even though the kid wore those same shoes the entire movie. I believed that when a cereal advertised itself as part of a complete and healthy breakfast, that meant no matter how sugary and sweet and teeth-rotting it could possibly be, that meant it was actually healthy, ignoring the fact that really the healthy part was everything else in the picture. And now, over the years, I think I've grown up a bit. I've had some experience, and I think I'm less naive and less gullible. And maybe actually even an adult, but that's debatable. But one of the things that has happened is that I've understood that, throughout life, you'll get various guarantees. Guarantees that kind of build that foundation that you can build upon, those assurances and promises and security blanket that, I can rely upon this for what I need to accomplish. And as I've entered the professional world, we start to get lots of different guarantees throughout everything. And they're kind of pitched to us through various aspects. It could be from vendor pitches telling us to, hey, buy this software or use this technology we provide. It'll totally make your life easier. It could be from conference talks showing us new and exciting open source technologies or research that, is a breakthrough that's totally going to make our lives easier. It could be project documentation, just kind of incentivizing us to take one more step or to adopt that project. Or it could be from companion teams that go and have new and cool ways of solving problems, and they're encouraging adoption. And in each of these different guarantees, they're kind of providing different things and speaking in different ways. Sometimes they're speaking in very markety terms like fastest or write it once, run anywhere, or it's the best at some arbitrary criteria. Sometimes they're kind of advertising simplicity. We can do it with a single click, or it's a push button deployment, ignoring the fact that more than likely you had 2 weeks worth of configuration files you were trying to write just to get it going. Sometimes they're ambitious in saying, we can solve all of your problems, despite the fact that, they might be varied and different, but you know what? We can handle them all. And we kind of build up this kind of false sense or this doubt sometimes that says, can it really do that? Are they really just selling us stuff? Are they really just kind of lying to us and that these guarantees aren't really true at all? And the answer is no. All guarantees are not lies. Now, there are a few cases where, of course, some things are vaporware and don't exist, and they just hope you coming along for the vision and the ride, and it will eventually materialize. And those probably could be interpreted as lies. But really, most of the time, we're giving guarantees are specific to what those individuals are providing. There becomes this kind of sphere of what they actually are saying. Now, our problem and our difficulty is like what happens when what we're perceiving is drastically different. This is often where we lead to a lot of different problems, a lot of different misconceptions, a lot of kind of hurt feelings and animosity, when there's no overlap at all between the two different systems. And you know what? Usually reality exists somewhere in between. Sometimes in the case where there's this great disjointed nature between what they're saying and what we're perceiving, it's easy to make a decision to say, no, let's not continue. It's not the right tool. And that's great. We should probably do that. But sometimes, often is the case, and that's why we're listening to the pitches, there is some overlap between the two. There's a sliver in the middle of what we're trying to accomplish and what they're saying that has a little bit of grounded truth. And the problem is to recognize how much of that overlap we actually have. Because what happens is when there's this much that we perceive that they're not actually saying, it leads to us being disappointed or a lack of fulfilled desire or fulfilled promises at the end that really kind of just hurt us. It doesn't actually hurt them because they're telling the truth of what they're actually saying. It's our interpretation that's often wrong. And so as professionals, what we really have to do is work on kind of realigning what they're saying and what we're perceiving to have the most overlap as possible. Because there's often the case that this is when we will be successful, or this is when we will understand what actually has to get built to accomplish the various problems. And so as we kind of think about this, it's really like, how do we, with a guarantee that is too good to be true, how do we actually make it reach that fulfilled state? And the way we do that is we make sure we dig into the details. And there's lots of different ways to do that, but there's three kind of main themes that I'd encourage you to think about. The first one is that definitions matter. Let's take a hypothetical situation where I come charging into the room, screaming at the top of my lungs, in a state of emergency and panic, that I could use a cobbler right now. You might be thinking to yourself, great, I can help you. I know how to solve this problem. I will get you one right away. But the issue might be, which one are you going to get me? There are three drastically different things, from someone who's going to help repair shoes, to a nice cocktail to relax at the end of a stressful day, to just a comfort food of a dessert to kind of enjoy at the end of a nice big meal. If you gave me the wrong one, I'd be drastically disappointed, and it wouldn't help me with my emergency at all. And just to make sure that everyone is clear and kind of remove any definition ambiguity, I'd like to point out that if I'm ever in an emergency, there's a specific definition that is always going to be the K-base, no matter what. But in this silly example, you might think, well, okay, there's lots of definitions, but we're in computer science, definitions matter, where we go and we love to argue about semantics of everything. And that's often true. But we also use a lot of really vague terms. We say things like fault tolerant, which can mean anything from the fact of it recovers and resolves itself when an error occurs without human and manual intervention, to it just fails and it tells you it fails and that's good enough. Or some things are defined as web scale, which can basically mean it runs on more than one machine, or it can run on millions and handle lots of requests, but you also are going to pay more money than you possibly could imagine. Or you could say something like it's cloud first. What does that mean exactly? And these are very marketing, and you're like, yeah, those are vague. We understand because they're just marketing type terms. Nobody in the industry really uses them. But what if we tried to define a word that we use pretty commonly throughout different stacks? What if I asked you to define consistency? And here's 4 possible definitions that you might choose from, or at least 4. There's probably a lot of others. And there's subtle differences in meanings behind each one that vary. Sometimes it's talking about the order of transactions being committed, sometimes related to application semantics, sometimes it's database constraints, sometimes it's just making sure that an operation couldn't be broken up from other concurrent operations. Each definition is slightly different than the other. So which one do you use to define consistency? And if you think about it, it probably really depends on what problem space you're working in. So consistency means a lot of different things in a lot of different places. For example, if we think about the normal relational database world where things are defined as being ACID, consistency is a first-class word in that acronym. It means something in this condition. But there's other acronyms in the storage system relational database world as well, like the CAP theorem, which came out that basically said you can choose any of these 3: partition tolerance, tolerance to failures, consistency, availability of the data. And the theorem, of course, says that you can only have at most 2 of the 3 different choices. So what is it? Consistency is one of those key attributes. So if we have 2 different terminologies, ACID and CAP, and they both have the word consistency in them, obviously, since they also both apply to storage systems, they mean the exact same thing, right? Well, the answer, unfortunately, is actually no. If we look at the definitions and what they mean in their different systems, we kind of see that from an ACID standpoint, the first 3 definitions are what is meant by consistency in those terms. So that really actually relates to database constraints and application semantics. However, if we look from the CAP standpoint, we see that the thread is actually more along the lines of every read receives the most recent write or an error. And actually, there's even a more explicit definition. There's the definition saying that consistency in the CAP theorem really means linearizability. What does that mean exactly? And that's the kind of gets expanded into this kind of definition of if operation B started after operation A successfully completed, then operation B must see the system in the same state as it was on the completion of operation A or newer. Okay. And so we kind of think back to the 4 different definitions. We see that really kind of lines up a little bit with that last one, because it's not really related to transactions being committed, application semantics, or anything like that, but more along the lines of kind of atomic operations and their ordering and being able to break them apart. And so we kind of actually see that linearizability is more similar to atomic consistency. Well, what's atomic consistency? That's a new definition and a new term and a new qualifier. Atomic consistency is sequential consistency with a real-time constraint, meaning there's kind of, instead of it being loosely coupled and happens eventually, things are guaranteed within a certain time box. But I've now just introduced another type of consistency, which is sequential consistency. And that gets defined like something like this. And you kind of can see that there's this giant rabbit hole of what consistency could mean, or an entire spectrum as you go down different avenues of what consistency could mean. So it's not really sufficient to say something is consistent. You oftentimes need to say what type of consistency is there. And if you look at different documentation, you can actually see that there's different types of consistency that mean things to different actual models. There's data consistency, which means stuff related to the programmer in the system. And then there's also system level guarantees of consistency that kind of has to do with memory and the reading and the writing of the different messages. So we kind of have a case where even though now storage systems exist in multiple different worlds of distributed systems and databases, we now have kind of a merging of multiple different definitions. And this is highlighted in a couple different research papers that kind of talk about the fact that sometimes you get terms that come from the database community, sometimes from the distributed system, and they're drastically overloaded and mean lots of different things in different situations. And so the encouragement is to make sure you understand where the definition and what the definition is for the term you're basing your assumption and guarantees on. Because if you pick the wrong one, you might have very, very surprising behavior. So I'd heavily encourage you to look for the explicit definitions. Look for what they're defining and what they're providing, and avoid the vague terms if possible. Be explicit with the type of consistency that's being guaranteed. Don't just kind of simplify it and gloss over it. The next aspect to encourage you to look at is to read the fine print. So we all know the very common example of the famous band Van Halen that had a rider in its contract for how different concert venues should be set up for shows. And they were well known for kind of having some little interesting lines built in. The first one, and most commonly well known, was the fact that they wanted, as part of their munchies, to have M&Ms available, but absolutely no brown ones. And this was kind of highlighted as something being eccentric to rockers in certain time frames and, laughed about. But what's interesting is that the term and the reason for this was actually kind of built on the idea that if someone read the fine print of their writer enough to pay attention to M&Ms, they would also have read it enough to know and care about the big things related to running electrical cords or equipment setup or how the lights were handled to make sure that the band and all of its employees were treated safely and respectfully. And so while this example of fine print is kind of funny and had value, we also see there's other ones that are just kind of silly and frivolous, where AWS provides a service called Lumberyard. Lumberyard is used to build video games, and it has specific stipulations about what you can actually use that system for, banning things like nuclear facilities or military use. But of course has some funny, catchy lines in there as well that basically set, tongue-in-cheek says that in the case of a zombie outbreak, all things are out the window. You can go and use this software for whatever you want. But reading the fine print is important because it's also how you're going to understand the system that you're going to build. So I'd like to take you through an example. I was chatting with a friend of mine who works at a different company, uses cloud native services and all of that. And he was just talking about the different problems he was trying to solve. And specifically, we were talking a little bit about this presentation and different guarantees, and we kind of dug into what they were building. And in the simplified version of what they're building was basically a system to accept permissions, do calculations, and then proceed to propagate those permissions and access controls throughout the rest of the system. And they weren't sure where everything was propagating to, so they were building something kind of built upon a queue, where they get the permission changes, publish it to the queue, and the downstream consumer will pick it up, process it, and apply those actual changes. And they were looking through what was available, and they found the Amazon SQS service, or Simple Queue service. And it kind of has the nice marketing material talking about the limited throughput, best effort ordering, at least once delivery, and it fits what they need. Like, let's use this. It satisfies a lot of what we need. We can only focus on the services and we can keep going. And the basic workflow, if you're not familiar, is that you have the producers who are sending the message to this queue, the consumers who are reading the messages from the queue. But to guarantee at least once delivery, what happens is when you read a message, the message basically becomes hidden for a configurable amount of time. This ensures that if a failure were to occur, the message would become revisible and could be consumed again by a different process. But if you're able to successfully process the message, you can issue a delete and it goes away and everyone can proceed. And that's how it guarantees at least once delivery. And so they were looking at it like, hey, that's great. We push the message on, pull it off, everything will work fine. But they thought about, what happens in the case of failure? And so they were like, the downstream system could be down, calculations could fail, the message might be unprocessable. We don't want to kind of get stuck in this state of not being able to proceed and just kind of have everything jammed up. And they read the documentation about Amazon SQS, and they found out, you can easily plug in a dead letter queue. And a dead letter queue basically works by consuming the messages off of the queue. And after a certain number of attempts, if you still haven't successfully processed the message, it'll just kind of send it over to that queue, letting things continue to flow and kind of taking the log jams out of the way. Like, you know what, that works well. We can kind of set up some monitoring for that and continue to proceed. And they were looking then at the types of messages that would be sent, messages that would add permissions and remove permissions. And they were thinking about the workflow. Okay, we get somebody who adds a permission. Who cares about security? Let's give this user full read, write, execute permissions. Oh, wait, we actually don't want to give them all those permissions. Let's remove the executable permission. So now we're just down to read and write. Oh, you know what? They really just need read permissions. Let's remove the write permission and continue on. And so when they think about this scenario, what they really end up with is, okay, this user should just end up with read permissions. But they also realized that the order of the messages is important. Because if those messages got out of order, you have the adding of all permissions happen last, and suddenly you're giving this person too many permissions when they should have been more restrictive. And so what they did is they read more about Amazon SQS and found out that, hey, you know what? They have a FIFO queue. And that FIFO queue guarantees that order is preserved under certain conditions. It kind of guarantees that the message is delivered once and that no messages after that message will get delivered until the consumer has successfully processed and deleted it. And under certain conditions, it guarantees that duplicates are not introduced into the queue. So it'll handle this case and make sure that the messages are in the exact order and processed in them. Great, let's just turn on that, convert the existing queue, turn it on, and we're good. I mean, what could go wrong, right? And that's where the conversation with my friend kind of took a turn. They explicitly kind of called out and stated emphatically that the exactly once guarantee of SQS is a giant lie. And more specifically, even after they've kind of taken it to production, done a learning review, a correction of event, whatever you want to call it, my friend had kind of vowed never to touch it ever again. But I was sitting there going, well, why? Everything looked like it was lining up great, looked like it was going to process and work correctly. But if we look at this example, you might already see what could happen based off of some of the things I talked about with how the dead letter queue works and the visibility of timeout. Specifically, what you can think about is that, say that first message was being consumed and processed, but it got retried a lot of different times for who knows what. The access service is down or wasn't being successfully processed. Well, then it's going to end up in that dead letter queue. But then the follow-up message will get processed successfully, potentially, and and then we should end up in the final state where that user should have been able to read, but really that permission never got applied, so they got no permissions at all. And this isn't that bad in a security standpoint, but you can think about this being really significant if this was something tracking money in transactions. But so, whose fault is this? Is SQS really to blame because their guarantees don't actually all work together? And the answer is actually a little bit of my friend's fault. Because as I was reading about how SQS worked and looking through the documentation, I found this explicit line called out where they say, if you need exact ordering of messages and are using a FIFO queue, you cannot use a dead letter queue as well. And so it actually was, as emphatically in anger as my friend was at this technology, it wasn't the technology's fault. It was the fact that they had not read the actual fine print of what they were building. And the fine print isn't there to be a gotcha or an escape clause of blame and anything like that. Instead, you need to turn it into an asset. You have to think about, how does it define the boundaries of what is possible for what you're trying to accomplish? And specifically, as you're building something, design around the limitations of that system. How will you compensate for the problems that are going to be encountered? And more importantly, reading the fine print proactively as you're building something helps you to avoid stupid mistakes and horrible bugs in production. The last kind of concept I want to encourage is to understand the problem being solved. Every tool is kind of in technology is really built to solve one job. And it's not, you kind of can think about the old phrase that if the only tool you have is a hammer, everything is a nail, because all you can do is really smash with it. But the other thing to keep in mind is that just because you could use the tool to accomplish something doesn't mean that you actually should. As an example, a couple of years ago at a conference, someone did a presentation on how do you build a REST service using only the command line tools in Bash. It was a fun thought experiment, just really trying to prove something out and to stretch themselves creatively, not that they were actually encouraging it. But it was an example of trying to fit a set of tools into a problem space that didn't really make a lot of sense. And there's commonly a lot of cases, other places where people start to try to do the exact same thing. But the other thing to think about it is that every successful tool and technology that's ever been built started out with a specific focus of a problem. Now, sometimes ambitiously, people will look at these disparate number of problems and think, you know what, I can solve all of them in one way. I can build a single solution and it will do all of it. And that's very ambitious and very hopeful. But oftentimes the scope of that is quite large and it'll take a long time to actually deliver it. And specifically, what could happen in that meantime is that sometimes the problems move around and change. Sometimes the problems kind of move just a little bit, enough to be problematic and hard and not be able to solve it completely with the original scope of what you were trying to build. And then sometimes problems just absolutely disappear. They're no longer what we want to do and what we want to try to accomplish. And so you might have this extra white space of where you were trying to solve a problem and you built up this code and complexity and debt that doesn't do anything because that problem doesn't even exist anymore. But really, most open source technologies or other technologies that we're building on started more focused, trying to solve exactly one problem, and then evolving over time to incorporate more problems, and then additional ones. And that's why they had that very targeted focus on just those specific problems and just providing the value in those spaces. Sometimes the problems disappear, and we no longer have to worry about solving them. And sometimes the problems, as we mentioned, move so outside of scope that it doesn't even make sense for you to think that the same solution would apply to both of them. And it really should be a drastically different solution to solve that other problem. And this happens across lots of different technologies. And it kind of builds upon the well-known Gall's law, which basically says that every complex system always has evolved from a simple system that worked. And if we ever are trying to build a complex system from scratch, it's never going to work and probably can't be made to work. So we need to be encouraged by tools that do evolve, and more specifically are evolving in a way that aligns with the problems we're trying to solve, as opposed to hoping it'll eventually get there and we're going to try to shoehorn it in. If we look at Apache Kafka, it's kind of followed a very similar journey. It started out as a message passing system with its goal being to, as high throughput, low latency as possible, pass messages from decoupled producers and consumers back and forth with a broker in the middle facilitating. And if you're not familiar with Kafka, there's a lot of great presentations that go into detail about how it actually works, all the nitty-gritty details. But basically, you have the three different consumers, or three different parties: the producer pushing the messages in asynchronously, the consumer pulling messages out asynchronously, the broker in the middle kind of worrying about storing and replication and breaking down topics, which are kind of the major focus of how the messages are organized, into partitions that are smaller consumable bits. And the consumers can be zero or many, controlling kind of how their rate of consumption varies as well, marking and tracking progress as you will. And it works really well. It's used throughout the industry, supported by different cloud vendors and providers. And the project, though, has continued to evolve. Like, no longer are we just worried about the message passing in the middle. Let's try to solve the problem at the edges of getting data out of Kafka into another system, or getting data out of that other system into Kafka. And they've started to evolve to incorporate a project called Kafka Connect, specifically focused on tackling that next bit of problem and involving the whole ecosystem as a whole. Now, I want to take a quick pause to talk about guarantees. And this is important because these are guarantees related to distributed systems. These are terms used across the industry in a lot of different ways. And with these guarantees, they're kind of, in a sense, on a spectrum. You've got a most once guarantee, which basically says, who knows what's going to happen? Maybe it'll get there, maybe it won't, which is kind of the least reliable and, untrustworthy guarantee you could possibly have. You have the at least once guarantee, which kind of guarantees that, it's going to get there at least once. It might get there 100 times, 1,000 times. I don't care, but it's going to get there at least once. And then there's exactly once, which says it's going to get there once and it's only going to get there once. And if we think about all these things, people often quickly latch on to the last one, because it's a lot easier to reason about a message only arriving a single time. It makes our code simpler. We don't have to worry about edge cases, conflicts, what have you. Exactly once is great. But if we start to look at research, what we actually find is that it's not really possible. There's research like the FLP paper, the two generals problem, or the more general Byzantine general problem, that kind of talks about consistency in when failure is an option, which it is absolutely guaranteed to be in a distributed system. It's very hard to guarantee that the message was received or that a response was received, and therefore it was processed exactly once. So oftentimes, or explicitly, you have to send it again, which means you're violating exactly once. And the reason I took this segue is, what's interesting is the Kafka ecosystem and the Kafka project began to evolve and suddenly guaranteed exactly once. And you're thinking to yourself, wait, I just said that wasn't possible. So what exactly does that mean? Well, the first thing is probably a bit of a confession. Sorry, let me take a step back. It especially becomes hard to think about because the fact that asynchronicity is kind of at the core of the infrastructure. It's how they get really high throughput and really low latency trying to pass messages throughout the whole system. So if I'm asynchronously sending messages, I don't know if the broker has received it or not until I get that ACK back. but I might not successfully get it, so I might have to send again. And vice versa on the consumer, as it's processing and consuming messages, the broker might not know if it successfully has read something and might redo it again. So I want to take a step and actually take a pause and talk about exactly once, because that's what the guarantee is actually providing, right? And I probably didn't do a good job of defining these guarantees, or I intentionally kind of building on the idea of definitions matter, didn't do a good job of defining what this guarantee is providing. And so all of the research paper that kind of discredits the idea that exactly once isn't possible is really kind of focused on something specific. It's specifically talking about message delivery. And the reason I qualify this is that exactly once delivery is different than what Kafka is claiming with exactly once. Kafka is actually claiming exactly once processing. But even that's not actually a good enough definition for what Kafka is saying it's providing. It's actually saying it's providing observably exactly once processing. And you might be thinking to yourself, what is that? We can do a quick example. Say we have a very simple program that looks like the following, and all we're doing is calculating the value of x. We can kind of see that, okay, execute the first line, then the second line, and our result is 10. We executed everything exactly once. We have exactly once processing. Perfect. That makes sense. That's what we're actually reasoning about. But what if I gave you a program that looked like this? You can kind of see that I'm calculating the value of x 10 different times. But the final result, no matter how many times I'm actually calculating it, is always the exact same thing. So I'm basically providing observably exactly once processing. You don't know how many times I actually executed through that loop. You just know that the outcome is the exact same. And this is a key foundation and fundamental idea in distributed system processing, because machines across the entire network can fail, different things can get restarted, what have you. And what usually isn't the guarantee that you only process it a single time. It's that no matter how many times you process it or reprocess it or recover from processing, you always end up with the exact same result. And that's how we get observably exactly once. Okay, so Kafka's being kind of finicky about how it's defining exactly once, and that's okay. But we still kind of have questions about how does it, if it's fundamentally built on the idea of message passing, so one system sending to the other, how can we have any sort of guarantees at all? How do they practically be able to implement this? So, because failure can occur both inside a machine, lots of different ways, but especially as messages are being passed between machines. And the first way that Kafka tries to solve this is through idempotent producers, right? I can guarantee exactly once if there's only one version of the message available. If there's multiple versions, it's really hard to guarantee that exactly once. And so with idempotent producers, Kafka starts to kind of build in some conditions. Specifically, messages being sent from the producer could be tied to a producer session, and they have to be targeting a single Kafka topic partition. So even not just a topic, but a specific partition. And so by tying all this extra metadata together, having some conditions being available, the broker can actually start to remove the duplicates that get sent under certain qualifying conditions. If you don't satisfy these conditions, then you don't have idempotent producers, and you could end up with duplicates in your system. But Kafka, reasonably says that performance-wise, this works under those specific fine print conditions. The other problem is, okay, what happens when things are partially happening? So maybe I'm sending messages to lots of different places, not just a single partition, but lots of different topics. So Kafka introduced the idea of transactions. And how do transactions work is that by basically they write a start and stop message at the beginning and the end of the transaction, grouping all the messages related to the transaction in between those messages. And so then if a transaction fails or needs to get rolled back, that stop message is never sent, which means that everything inside of that transaction basically gets thrown away. But you kind of have to have some configuration and agreement from the consumer side of things. You need the consumer to not care about any of the messages unless they're inside a fully completed transaction. So that consumer has to build in some configuration. Kind of, they have to go essentially into la la la, not listening to any of those messages in the middle. So we actually kind of see it, well, the pre-existing goal of Kafka, which was to have a really loose coupling between producers and consumers and the broker, become a little bit tighter. You have to have an agreed upon state and contract between all of them, and all of them have to have the right configuration in place for this system to possibly work. If any of them don't, then kind of the exactly once guarantee of processing goes completely out the window. But technically, it's not just any producer and any consumer. Really, if you kind of look through what they're guaranteeing and saying is possible, is that they're saying it's possible for very simple processing applications. And I say simple, it's very much the heavy lifting of the industry of read, process, and writes, basically reading from Kafka, processing it, and writing out to another Kafka topic. And specifically using what's now kind of the next evolution of Kafka, which is a processing library that sits on top as a consumer or producer, making things easy to develop in theory. But what's interesting is it's not just that if you use their stream APIs, you get this guarantee. Kind of, they even define that the problem statement is specific to certain cases, and not all of the possible code you could write with the streams API would equal or provide exactly once guarantees with regard to processing. So even using the API itself doesn't give you those guarantees. It has to be under certain conditions. And they kind of further highlight that if once you try to get your data out of this system or out of that very simple processing, you kind of lose those guarantees as well and are relying upon the external systems. So if you're materializing into a NoSQL database that doesn't have transactions, you could be in a situation where exactly once processing isn't actually possible because it's not just in the confines of that simple application, but really it's an end-to-end guarantee. And you need your application and your whole system to provide that guarantee. So what we kind of see is that this entire problem statement, while it seemed very grand an idea of what could be accomplished, really was specific to a very targeted use case and a targeted application. Now, it's an important building block for the rest of your system, but their guarantee is just within that focus. So the encouragement is making sure to understand the problem statement so that you can kind of understand, does what I need and what they're providing actually overlap? And importantly, identifying the discrepancies between the two different systems. Because when you identify the discrepancies, you can decide, well, can I live with them? Or do I have to build something to compensate? And is what I'm building worthwhile or complex or error prone and not worth the agony and the problem? I should really think about a different set of guarantees or a different set of technologies. Now, hopefully, throughout this entire presentation, I haven't given you a lot of doubt or despair or lack of trust in what other teams provide, because I don't want you to think that all is lost. The encouragement is that these tools will help you to dig deeper and understand what you're actually adopting. So the next time you kind of are sitting and thinking to yourself, hey, should I adopt this technology? I strongly encourage you to kind of pour yourself a nice bowl of healthy, sugary cereal and sit back and kind of evaluate the technology about all these different aspects to make sure that you are using the right terms, you understand the fine print, and you have aligned that your problem and the problem being solved are in agreement about where things are headed. If you don't believe me that these things will help to remove some headaches, take the word of this industry expert who calls out that there's lots of things in the world that do magic, and you think that they're going to do exactly what you were planning to do. But if you don't dig into the details and understand, you'll end up with a huge headache or figuring out how to get what you want and just have a bad time. I'd like to thank you for your time in this presentation. Here's a lot of references related to everything throughout the rest of the presentation. Thank you for your time.